Hey guys, so now we are moving into our fourth lesson of space, which is a lesson on stars. Okay, so what are stars? They are giant balls of hot gases that produce and emit energy as light energy. So we've talked a little bit about stars already. We know the sun of our solar system is a star. So this is a giant ball of hot gas that produces energy. We've talked a little bit about how a reaction occurs at the very core of stars that produces this energy called nuclear fusion, and we're going to go into a little bit more detail on that in this lesson. Okay, so there are different characteristics of stars or ways that stars can be classified or compared and differentiated. So these include brightness of the star. So we will see in future slides how some stars are brighter than others based off of their luminosity. Temperature of stars. Okay, some stars are hotter, some stars are cooler. Color of stars. Some stars are red, white, yellow, blue. Okay, a blue star has a higher temperature, is hotter, whereas a red star has a lower temperature, is cooler. Stars are of different sizes. Okay, we can compare star size. The age of a star. So we're going to learn that lower mass stars, so stars that are smaller or have a lower mass, live longer than, say, a massive star that has a higher mass. And also distance from the Earth. So how far the star is from the Earth. Okay, so the brightness of stars, this is described as luminosity. Luminosity is the total amount of light produced by a star each second. Okay, so brightness of a star, luminosity, the amount of light produced each second. Luminosity, or the brightness of stars, is measured by comparing the star's luminosity with the luminosity of the sun, which is 1. So there's this like scale, or this grading scale, where in terms of luminosity, the sun has been assigned a 1 in terms of luminosity. So Sirius is the brightest star with a luminosity of 22. So if the sun has a luminosity of 1 and Sirius has a luminosity of 22, that means that Sirius is 22 times brighter than the sun. The closer the star is to the Earth, the brighter it seems. That is why the sun is so bright, because it is quite close to the Earth. The further the star, the more spread out. So you'll see over in this little picture here, Sirius is that bright star there. That is like the brightest star with a luminosity of 22. And if we look up here at this graph, okay, we've seen this before. Remember, on the x-axis we have temperature, and on the y-axis we have luminosity or brightness. Okay, so a star that's up here, okay, so this blue star is very hot and very bright. Whereas this star over here is not as hot, it's less hot, and it's less bright. Okay, so remember how we use graphs, so over, okay. Okay, so if we had a star over here, okay, that's going to be a star that is very bright, but not as hot. Okay, and then whereas over here, this would be a very hot star, but less bright. Okay? Okay, so now we're going to look at magnitude of stars. So this very much has to do with the size of the stars, as well as other things. So it says here, cooler stars are smaller than hotter stars. So the smaller the star, the cooler it tends to be. But magnitude, we have two different types here that we're going to compare. So we have something called apparent magnitude, and this is how bright a star appears to be. Okay, so if you were standing in your backyard and you're looking at the stars in the sky, if you were to say, oh, that star appears or looks to be brighter than that star, that is apparent magnitude. Okay, so even if you look over in this diagram here at apparent magnitude, you'll see 4 different stars. We have star 1, which is really tiny, doesn't look very bright. Then we have number 2, which is not as tiny, but still small. 3 is this pink star, and 4 is this yellow star, and it says, number 3 appears to be the brightest. So from where this person is standing, looking into the sky, comparing these 4 stars, number 3 is appearing to be the brightest. So that's using apparent magnitude for this star, whereas absolute magnitude is the amount of light a star would give off if they were at the same distance from the Earth. Okay, so this is like looking at the same 4 stars, but making sure that they're all at the exact same distance from the Earth and then comparing them. Because we need to keep in mind that a star that is closer to the Earth is going to appear brighter or bigger, whereas a star further from the Earth is going to appear maybe smaller and not as bright, but that might not necessarily be the case when you really just compare those 2 stars from the exact same distance from the Earth. So down in this diagram, absolute magnitude, you'll see all 4 of the same stars, okay? But now star number 2 looks a lot bigger and brighter than star number 3 because it's brought to it the same distance as star number 3. All the stars are at the same distance from the Earth. Okay, so the second diagram is kind of showing the fact that, oh, well, if they're at the same distance from the Earth, number 2 is bigger and brighter than number 3, whereas with apparent magnitude, 3 seemed the brightest. Okay, color and temperature. So color of a star is related to the surface temperature. Okay, guys, so color and temperature are directly related. The coolest star is red in color. A star that's warmer is going to be yellow. And then a star that's considered hot is white in color, and the hottest stars are blue in color. So remember, guys, down here on the X is temperature, okay, and temperature increases from right to left. So this is going to be a hotter temperature over here. This is going to be cooler. So this makes sense. So we have red, okay, closest to the right, red, which is coolest in temperature. Then if you start to move to the left, you'll start to see more yellow stars, okay, so they're considered warm, temperature is increasing. Then we're getting into white stars, which are hot, temperature is increasing even more. And then as we get right to the left here, which are the hottest stars, we see the blue stars, okay? The sun, specifically, our sun in our solar system, is a yellow/white star. Okay, so this is a temperature of 6,000 degrees Celsius approximately. Okay, so about right here, okay, is our sun. Okay, so if we come down, okay, that gives us an approximate 6,000 degrees Celsius. Okay, composition of stars. Every element emits unique ranges of colors called an emission spectrum. So stars are composed of different elements. Okay, an emission spectrum is when an excited electron moves to a higher energy level or orbital, and when it falls back to its ground level, it emits certain colors of light. So we learn this in chemistry that elements are made up of atoms. So if we're talking about the element hydrogen, hydrogen is made up of hydrogen atoms, and we learned our Bohr-Rutherford diagrams. So the structure of an atom is a nucleus with those orbitals or those shells around the nucleus. So over here, this diagram, you'll see the emission spectrum of different elements. So we have hydrogen, helium, lithium, oxygen there, and these emission spectrums, different wavelengths of light that are emitted. Okay, so in order to determine the chemical composition of a star, you can use something called, astronomers use something called a spectrograph. Okay, and this is an instrument used to tell us what the star is made of. So specifically, a spectrograph can tell us how much of each element the star contains, the temperature of the star, and which direction the star is moving relative to the Earth. Okay, so we'll talk about that a little bit later. It's called redshift, blue shift. That tells you if a star is moving towards or away from the Earth. Okay, but again, these spectrographs are used because specific gases emit specific colors. Okay, and when we use a spectrograph, this creates the emission spectrum for the star, and there are specific emission spectrums for different elements. So you'll see down here it says dark absorption lines. So these black lines are known as absorption lines, and they show the different wavelengths that are emitted. This can help determine the composition or what elements a star is made up of. So here are just a couple diagrams here, okay, showing emission spectrums for different stars. Okay, and down here is an actual example of a spectrograph. Okay, so I'm gonna show you how the emission spectrums of different elements are used to help identify the composition of a star. So this is star number 1 here, guys, and these are the emission spectrums, and these black lines are these absorption lines. And when trying to determine the composition of a star, we can compare these black lines of the star to the black lines of the emission spectrum of each element, and when these lines match up to the lines on the star, then you know that that star is made up of that element. So let's do star number 1 together. So you'll notice that we have this dark black line right here. So I'm going to come over to hydrogen, helium, sodium, magnesium, calcium, and iron, the emission spectrums for them, and I'm going to find one that has that exact dark thick line in the same position. So just one line. Okay, so if I look through all of these, I will see that line right here as well. Okay, if I then start to compare a little bit further, I see this line matches up with this line, and so on and so forth. This line matches up with this line. Okay, so I know by comparing the absorption lines on both emission spectrums that star number 1 does in fact contain hydrogen. Okay, now I know star 1 also contains something else because I have, say, this line here. Oops. I say I have this line as well. Okay, so now I also want to find another element that might match up that line. So if I look over here, of all of the emission spectrums, I can see that hydrogen, that line matches up with the line or the absorption line on star number 1. Okay, then I also have this line which matches up with this line. Okay, and then I also have these lines that match up. Okay, so by matching up the absorption lines, that's going to tell you what element the star is composed of. Okay, so again, this is the emission spectrum for the star, and we're going to compare those lines to the emission spectrums of each element to see what the star is made up of. So I can also say that this star is made up of helium. Okay, if I do star number 2, guys, this one's actually a little bit easier. So if we try to compare the lines on star number 2, again, I'm just going to start with this double line here, and if I look over to my elements, the only spectrum that has that double line there is this guy right here. Okay, and then if you look, you'll notice that all of the lines actually match up. So the rest of the lines also match up, Okay, so we could say that star number 2 is actually only made up of helium. Oh, sorry. That's wrong. That's not helium. That's the one below, which is sodium. Okay, so this is how you use the emission spectrums of elements to help identify the composition of stars. Okay, so why do some star spectrums seem shifted? We know everything in the galaxy is moving. If the emissions are shifted to the red end of the spectrum, the star is moving away from the Earth. This is known as redshift. Okay, so when the emissions are shifted towards the left, okay, towards the red side of the spectrum, that tells you that that star is actually moving away from the Earth. So redshift is moving away from the Earth, whereas if the emissions are shifted to the blue spectrum, or the blue end, which is to the right, that means that the star is moving towards the Earth. Okay, this is known as blue shift. This should say shift. Okay, so if we come down to see this example, if you look at this middle spectrum here, guys, you'll notice, let's say, let's use white. Okay, see this guy right here, these absorption lines. If we look up to the top spectrum up here, you'll notice that those absorption lines have shifted to the left a little bit. Okay, so they've shifted towards the red end of the spectrum. That tells you that that star is moving away from Earth. Whereas if we come and look down here, okay, those absorption lines have shifted to the right with the blue end of the spectrum, which tells you that that star is moving towards the Earth, which is known as blue shift. Okay, so now we'll look at the mass of stars. So there's something called solar mass, and that is the mass of the sun. So the mass of the sun is 2 times 10 to the power of 30 kilograms, okay, also known as solar mass, the mass of the sun. So this is like saying 1 solar mass. Okay, so the sun is 1 solar mass, and that is really equal to 2 times 10 to the power of 30 kilograms. Okay, we use solar mass to compare the mass of other stars. They can be from 0.1 to 120 solar masses. Okay, so again, we use the scale where we assign the sun as 1 solar mass, which is equivalent to 2 times 10 to the 30 kilograms, and then we use that to compare the masses of other stars. Okay, this also says, note, big mass does not always mean big in size. Okay, so remember, there can be a smaller star that is very, very dense, okay, and so density is going to play a factor when it comes to mass and size. Okay, so you can have a smaller star with a greater mass in comparison to a larger star with a smaller mass. Okay, so now we're going to get into the life cycle of stars, guys. So this is a few slides. Stars in general last and live for billions of years. Okay, so there is a part of the life cycle where stars are born, and then there's a part of the cycle where it's the death of the star. Okay, mass determines brightness of stars. Okay, and mass also determines the life cycle of a star. So we're going to learn that a lower mass star lives for longer than a higher mass star. Okay, so the life cycle of stars. Stars are born. So guys, there are 3 steps involved in the birth of a star. So the first step is called the nebula. Okay, what is the nebula? This is a massive cloud of interstellar gas and dust. Okay, so this is an area in space where there's a whole bunch gas and dust in an area, and then over time parts of this nebula, so parts of the gas and the dust, starts to collapse in on itself. When enough of this material collapses in on itself, this starts to form something called a protostar. So when the nebula gains enough density, it develops gravity. So once gravity has been developed, this pulls more and more and more material in, which then causes a greater density. Okay, so the gravity causes the gases and the dust and the material to collapse in on itself further. This creates a star that is denser and denser and hotter. And eventually this material is so close together that it then starts performing the chemical reaction called nuclear fusion. And this is where the star actually gets its energy and it is able to glow. Okay, but the first two steps starts with a nebula. Okay, so the nebula is just a cloud of gas and dust that starts to collapse in on itself. Okay, and then once enough of that material starts collapsing in, this allows the nebula to gain more density, and once it becomes more dense, it develops gravity, which becomes the protostar. And once there's gravity, that pulls more and more and more material into the center, which causes an even greater density. Okay, as the protostar gets more and more dense, eventually it's able to start nuclear fusion. Okay, so that will bring us to our third step of the birth of a star. So nuclear fusion is when the center of the star becomes hot enough that nuclear fusion begins and the star glows. Okay, so once enough of that material has been pulled in on itself and that gravity starts to take over, pulling even more material in, okay, we go from a nebula to a protostar, and then once that star becomes dense enough, nuclear fusion starts to occur. And now nuclear fusion specifically is the fusion of hydrogen atoms to form helium atoms. Okay, so this is the process or the chemical reaction that gives stars its energy. So hydrogen plus hydrogen makes helium, and this reaction gives the star energy and allows it to glow. Okay, so all stars, no matter the mass of the star, it could be a low mass star or a high mass star, are going to go through those same three stages for the birth of a star. So nebula to protostar to nuclear fusion, where it then starts to burn for millions of years. Okay, so once nuclear fusion starts occurring and those hydrogen atoms are fusing to form helium atoms, the star is burning for millions of years. How a star will die is dependent on its mass. Okay, so the more mass of the star, the faster its rate of nuclear fusion, so the faster it uses those elements that are inside the core of the star. And once the hydrogen runs out, eventually the helium starts fusing to form carbon, and then once the helium runs out, it goes on and so forth. So how a star will die is very much dependent on the size of the star. A bigger star or a higher mass star is going to have a shorter life cycle. Okay, and there are two different ways that stars can die. Okay, so stars can die a certain way based off being a low mass star and a certain way based off being a high mass star. So we're going to get into that now. So we're going to move into death of a star now, but please remember, birth of a star is the same no matter what. Nebula to protostar to nuclear fusion. Okay, so first we're going to talk about death of a star for a medium-sized star. Okay, so there are different steps involved in medium compared to large-sized star, or low-mass star is like a medium-sized star. So after burning for billions of years, available hydrogen has turned to helium. Okay, so remember we said nuclear fusion occurs, and that's where hydrogen atoms fuse to form helium atoms. Okay, but eventually that hydrogen runs out. Okay, and when that hydrogen runs out, a helium-rich core becomes surrounded by outer layers of hydrogen gas. Okay, so now the core is helium-rich, and the helium gases have kind of drifted away from the core. The core begins to contract and heat up. Hydrogen then also heats up and expands outward. Okay, so hydrogen was at the core, it was fusing to form helium for the energy. Now the hydrogen is expanding outward, and the core is made of helium. Okay, and when that hydrogen expands outwards, this causes the star to become something called a red giant. Okay, so when hydrogen runs out, helium atoms fuse to make carbon and oxygen, and this creates more energy and causes the outer layer to expand. That outer layer is made up of hydrogen, and when that outer layer expands, it becomes a red giant. Okay? Then after that, eventually, the outer layers start to drift away, expanding to produce something called a planetary nebula. Okay, so this is when the star starts to lose hold on its outer atmosphere, and the outer atmosphere starts to drift away, which is the planetary nebula. Okay, so up here, guys, you'll see the red giant. Okay, it's actually really interesting because our sun is considered a low mass, medium-sized star. And in approximately 5 billion years, our sun will become a red giant. So it will expand so far out that it will actually swell and eat the first 4 planets of our solar system. So in 5 billion years, those first 4 inner planets will be consumed by the sun because it will become a red giant. Okay, and then down here is when those outer layers start to drift away, and it then becomes a planetary nebula. Okay, eventually, once the outer layers drift away, all that's left is the white dwarf. Okay, it's called a white dwarf. This is the dead remnants of a star. It's a very dense object. So the white dwarf is when no more nuclear fusion is occurring. Okay, so this is just the core that's left over from the star, and all of those outer layers have drifted away. Okay, it's dense, and there's no more nuclear fusion happening. After many, many, many years, the white dwarf then cools. Okay, there's no more nuclear fusion, so it's not creating energy anymore. So the white dwarf eventually cools, and what's left is just dark, cold matter, and that's known as a black dwarf. Okay, so in order, birth of a star is nebula to protostar to nuclear fusion. Okay, that's the birth of the star. And then for a low mass star, eventually it becomes a red giant, then a planetary nebula, then a white dwarf, then a black dwarf. Okay, now we'll talk about death of a large-sized star. Okay, so again, based off of mass. So large-sized stars have a shorter life cycle because they use hydrogen faster than low-mass stars. When the hydrogen is used up, helium begins nuclear fusion. Okay, so we saw that in low-mass stars, hydrogen gets used up, helium begins to fuse to form carbon and oxygen, but the large-mass star uses elements all the way to iron. Okay, so the large-mass star undergoes nuclear fusion all the way until the element iron. Once this happens, all of those outer layers start to drift away, and this causes the star to swell to a red supergiant. Okay, in low mass, it was a red giant. In high mass or large star, it's a red supergiant. Okay, and this swells to become much bigger because these stars are using even more elements for nuclear fusion, so there's more layers of gases that are drifting away, causing it to become extremely large. Okay, once a large-sized star swells to a red supergiant, no more nuclear fusion occurs and the core collapses on itself, which causes the rest of the star to collapse on itself. But what happens is it bounces off, okay, and it's like a huge shock wave, which is like a supernova explosion. Okay, so swells to a red supergiant, star collapses under its own gravity. Okay, so now no more nuclear fusion is happening. Okay, and what I want you guys to understand is that when nuclear fusion is occurring, there's energy being created that allows a star to be alive. But once that energy stops, gravity takes over, which pulls everything back in and causes that star to collapse in on itself. Okay, so that happens, but then there's like this huge rush that bounces back out and the outer layers explode, known as a supernova. Okay, then what's left behind after the supernova is something called a neutron star. So guys, there are two routes that a high mass star can take. After a supernova, it can either become a neutron star or a black hole. So first we're going to talk neutron star. This is the core that's left behind when a star over 10 solar masses collapses. Okay, so based off the size, if it's over 10 solar masses, it's going to become a neutron star. It's the core that's left behind. All those layers of gas are gone. It's extremely dense and tightly packed with neutrons. So it says here, in terms of the mass of a neutron star, the weight of one spoonful, so the weight of one spoonful of a neutron star is equivalent or equal to the weight of Mount Everest, guys. So that tiny little bit of a neutron star is so dense that it has the same weight as Mount Everest. Okay, and the gravity of a neutron star is 300,000 times greater than Earth. Okay, so that's one route after a supernova is a neutron star. Okay, just that dense core that's left behind. The other is a black hole. Okay, so the black hole occurs in the largest of stars. Okay, the star collapses under its own core, creating a black hole. Okay, so again, there's no energy being created, so gravity takes over, causes the star to collapse. The matter is so dense and the gravity is so strong that not even light can escape. Okay, pulls in any nearby matter. Okay, so the black hole happens in the most massive stars. The core collapses, the gravity is so strong that it becomes a black hole. Okay, so now we're going to do a little bit of review, guys. So the life cycle of a star. So we start out with this nebula. Okay, so remember, in the birth of a star, we start with a nebula that then turns to a protostar, and then nuclear fusion starts happening. That's the birth of the star. Okay, so that's us here. Okay, and then if it is a low mass star or a smaller star, it burns for millions of years because it's undergoing nuclear fusion. It's using those hydrogen atoms to fuse to form helium atoms, and it's giving the star energy. Okay, but once that nuclear fusion stops, a low mass star goes to a red giant. Okay, then from a red giant, it turns to a planetary nebula. Okay, then from a planetary nebula, it turns to a white dwarf, and from a white dwarf, it turns to a black dwarf. Whereas stars that are high mass stars or larger stars, again, burn for a very long time, not as long as low mass stars. And once that nuclear fusion stops, these high mass stars start to die and they become or swell into a red supergiant. Okay, so again, remembering those outer layers, the outer atmosphere of the star starts to drift and expand away, causing it to swell. Okay, then becomes a supernova. Okay, and then high mass stars are either going to become, from a supernova, a neutron star. Okay, and then the largest of stars, a black hole. Okay, and again, there's just different diagrams to show the same thing. Okay, and this is depicting the exact same thing. It's kind of just remembering that the birth of a star is starting with the nebula, which is just that big cloud and massive cloud of gas and dust, and eventually it starts collapsing in on itself, and once it gets dense enough, gravity starts to take over and it makes it even more dense, okay, and then nuclear fusion occurs, which provides the star its energy. It burns for millions of years, okay, and this low mass star, so that's going this way, once it's burned and it starts its death, becomes the red giant, okay, those outer layers swell and drift away from the core, okay, and then becomes a planetary nebula, white dwarf, okay, where all that's left is the core, okay, and then cools to a black dwarf, okay, which is just cool dark matter. In the high mass star, same birth, nebula to protostar, nuclear fusion occurs, burns for years, and then becomes a red supergiant, okay, once it's run out of its energy and nuclear fusion isn't happening and those outer layers start to drift away, then becomes a supernova, and then from a supernova, if it's the biggest of stars, it will become a black hole, and the other option is that it becomes a neutron star. Okay, so again, guys, a quick recap. I know we've been going over it many times, but medium-sized stars. Number 1, nebula concentrates into a protostar. Then nuclear fusion occurs, the star has its energy, it's making light and heat, burns for millions of years, eventually nuclear fusion stops, and death of a star starts happening. So in a medium-sized star expands to a red giant, explodes into a planetary nebula, then it becomes a white dwarf, okay, so just that core, hot core left over, and then it cools into a black dwarf. For a large-sized star, nebula concentrates into a protostar and nuclear fusion occurs, same birth, okay? Once that energy runs out, death of a star occurs. Large-sized stars expand to a red supergiant, explodes into a supernova, and then from a supernova either becomes a neutron star or a black hole. Okay, and here's some videos for you guys to be able to watch just to kind of solidify those concepts. Okay, and as for STARS practice or homework, you guys have some practice worksheets on pages 14 to 15 in your space booklet. Thanks, guys.